going to be looking at the rest of 3.1i, just to make sure you feel good about it all. If you already feel good about it and you're like, I don't need it, then you could start working on 3.2a, which is a review of dilutions. Okay, so if you're like, I'm all done with this, Ms. Spence, I don't need it, then you can take a look at dilutions, which we are just reviewing in order to get to our next section. All right, so we got partway through. This is on, what page are we on? Let's see. This is on page somewhere, 2040. Page 39. And we were looking at changing the solubility of calcium hydroxide by changing the ion concentrations, okay? So we had gotten partway through this list, and then we ran out of time and the bell went, okay? So if you add sodium chloride to this equilibrium system of calcium hydroxide, what do sodium and chloride not do? We only got halfway through the sentence. They do not react. And therefore, is there any shifting? Therefore, no shifting. Therefore, the solubility does not change. What if we add HCl? Joyce? Yeah, the OH reacts with the hydrogen. Okay, so we get H plus OH minus gives us H2O, and therefore our stress, what is our stress? Concentration of OH minus decreases. Therefore, the system shifts to the right. And what happens to our solubility? It increases. What if we add Na2SO4? Oh yeah, for sure. SO4 combines with the calcium. Yes, it does. If you look on your table of solubilities, you can go here and you can say, what does sulfate do with calcium? Well, it is low solubility. So Ca2 plus SO4 2 minus gives us CaSO4 solid. So that means that our stress then is that the concentration of calcium does what? Decreases. And if it decreases, we are shifting to the right and the solubility increases. Now you should note that you can always decrease hydroxide by adding an acid. I think you guys are getting really good at recognizing that, okay? This one here is something new, possibly for you. You may know this from before or you may not. You can always decrease carbonate by adding an acid. The H will react with the carbonate, producing H2CO3, but it doesn't just stay as H2CO3, it then undergoes decomposition into CO2 and water. I don't know why I didn't write that in there the first time. But it's kind of nice to think of it as a two-step process because it's really easy to see how these two guys get together to form H2CO3, yes? And then once they are together, they can decompose into carbon dioxide and water. So is that worthwhile memorizing? You know, if you're okay with losing 1 mark, possibly, or possibly no marks, because it may or may not come up. It's not a big deal. Do you know what I mean? It's something that it is useful to know, but if you don't remember it, it's not going to be a big part of your mark, okay? And you can always, well, not always, you can sometimes decrease some ion concentrations by adding something that will precipitate them. If you decrease the concentration of an ion, decrease concentration of an ion, will the solubility increase or decrease? So that would be like we decrease the concentration of a ion. Solubility will increase because it shifts right, absolutely. And conversely, if you increase the concentration of an ion, the solubility will decrease for the same reason. If we have our AB salt in equilibrium with A plus and B minus, and we increase, say, the concentration of B, it's going to shift to the left and our solubility will decrease. Now, so far we've been talking about adding things to a solution that's already present of the calcium hydroxide, but maybe instead you have a beaker full of water, you have a beaker full of sodium hydroxide solution, and you have a beaker of acid solution. And now you're going to take some solid calcium hydroxide and try dissolving it in each of them. It doesn't matter whether you've dissolved the calcium hydroxide before and you're adding in those extra ions, or if you have those extra ions in solution and then try dissolving the calcium hydroxide. It still has the same effect on the shifting of the equilibrium. So what that means is that you will sometimes see questions like this. In which of these solutions will you be able to dissolve the greatest mass of calcium hydroxide? So I've got 4 beakers, I've got some calcium nitrate, I've got some sodium chloride, I've got some HCl, and I've got some NaOH, and I'm going to try dumping calcium hydroxide into each of those beakers, and we're going to see which one we can dissolve the most. So, in our first one, the calcium ion has been increased, yes. So that shifts it to the left, which means that the solubility has been decreased. So this has a lower solubility. So you would not be able to dissolve as much calcium hydroxide in a solution of calcium nitrate because there's already some calcium in there. NaCl, what does NaCl do? Nothing. So the solubility is just normal. When we have our HCl, what does H do? It reacts with OH and gives us H2O, and so our concentration of hydroxide has decreased. So that's going to shift this equilibrium to the right. What have we done to our solubility? Our solubility is increased, so the solubility is higher. And finally, we have our hydroxide ion here. So the concentration of OH minus is higher. So that's going to shift it to the left. So solubility is lower. So you can treat these questions just like you did the other ones. And you can go, okay, well, where can I dissolve the greatest mass? I can dissolve the greatest mass in the one that has the highest solubility, yes? So our answer then would be C. Now, it doesn't just matter what substance you're using, it also depends on the concentration, because in the next question, what we have is we have calcium fluoride. And all of these things are going to increase in ion concentration, yes? Our first one would increase the concentration of calcium, which would shift it to the left. Our second one would increase the concentration of fluoride, which would shift it to the left. And then we have fluoride again, and then we have calcium again. What's the only thing that's different here, though? That would be the concentration. The greater the concentration, the more the equilibrium will shift. Does that make intuitive sense? The greater the concentration, the more the equilibrium shifts. I hope it does. So in which of these would calcium fluoride be the least soluble? A, B, C, or D? Tell your partner. Once you've finished writing. So we're going to vote on this one. You get to vote either A. Are we good with A now? We know A. B, which is your palm and your thumb on your palm. And then C. C is nice and easy. And then D, just your pointer finger goes up. Okay? So A, B, C, or D. 5, 4, 3, 2, go. I got some A's, I got some C's, I got some D's. Okay, so let's take a look at this and decide. In this one, my concentration of calcium is 0.01. Yes? I didn't see anyone with a B. Did anyone vote B? Okay, so I'm going to ignore B. In this one, we have the concentration of fluoride is 0.001. And here we have the concentration of calcium, which is 0.1. So because this one is the largest concentration, it's going to cause the equilibrium to shift the most. Yes? Does that make sense? Yeah? No? If you think of it this way, like let's say we started out with calcium fluoride that was made by dissolving calcium and fluorine. So we would have, these are totally made up numbers. They're not right because calcium fluoride is low solubility, but let's say we had 1 molar calcium and we had, I don't know, no, 2 molar fluoride. Now, if we did a KSP for this, what would the KSP expression be? We're going to take our ions. We've got calcium 2 plus times fluoride squared. Yes? Now, let's say you know what? I don't even want to do it with calcium and fluoride. I want to do it with a 1-to-1 ratio because it just makes seeing it easier. Can we do that? So let's do it with calcium and 1.0 molar sulfate. There we go. So we take this and we say, all right, if I increase my concentration of calcium to, let's say, 1.5, no, not 1.5, to 2.0, what's going to be the new concentration of sulfate? It'll be, sorry? It'll actually be 0.5 because what we're going to have here is we have 1.0 times 1.0 gives us 1.0. And then if we have our KSP, we know KSP is 1. So 1 then is equal to our calcium, which is now 2.0 times something. So that's going to be 0.5. Okay? You don't really need to do this for now because we're not really doing the math, but that kind of gives you an idea of why the higher concentration makes more of a difference. And if it doesn't, don't worry about it. I feel like I've done a bad job explaining this, but can we move on? Yeah, okay. The common ion effect. I actually wish I didn't have to teach this as a concept with a name because we have already done the common ion effect. We go back here and we look at calcium hydroxide. Calcium hydroxide makes calcium ions, yes? If we add a substance that also contains calcium ions, that means these two substances have calcium in common. okay? So the calcium ion is common to calcium hydroxide and calcium nitrate. All the common ion effect says is if you add a substance with a common ion, it will decrease the solubility. But it's really just putting a name on a concept that you already know. Yes? But I find that because it just defining it makes it sound confusing and complicated. So if we go down, to the definition, the common ion effect is a decrease in solubility of an ionic precipitate. So let's say we're decreasing the solubility of silver chloride. So we're decreasing the concentration of an ionic precipitate by adding something that is soluble and so if I want it to be soluble, I could use something NO3 or I could use Na something because those are guaranteed to be soluble, yes? So I'm adding a soluble compound with an ion in common with the precipitate. Well, what are the ions in the precipitate? They are Ag plus and Cl minus. So we could say I could add AgNO3 and that would decrease the solubility of silver chloride because we have silver in common between silver nitrate and silver chloride. Don't get too hung up on the name and the definition. You know how it works. You have all been successfully describing to me how the common ion effect works already. So just at this point, just go, okay, that's what it's called. It's specifically for decreasing the concentration. I don't know why that gets a special name. And if we increase the concentration by adding hydrogen to a hydroxide compound, that doesn't get a special name. Okay, so it's only when you're decreasing solubility by increasing an ion concentration. All right, but you have to have heard the term because it will come up from time to time. Just giving you some examples of a whole bunch of ions or a whole bunch of compounds that have chloride in common. We have sodium chloride, aluminum chloride, potassium chloride, silver chloride, and calcium chloride. They will all affect the solubility of one another. And we just did that one, so let's skip over that. Does changing an ion concentration have an effect on the solubility of a compound? If I change ion concentration, do I affect the solubility? Yes. Haven't we just been doing a whole ton of questions where that happened? So yes, just like all the questions. But the reason I'm asking this one, sorry, yes. The reason I'm asking this one is because what I really want to ask is, does changing an ion concentration have an effect on the solubility product constant? And before I call on you, I'm going to give everyone a chance to just talk about this a little bit. So talk with your partner. Does changing the ion concentration change the KSP? All right, what do you guys think? Yes, no? No, why not? Exactly. So number one, we know that KSP is a constant, therefore it won't change unless we change the temperature. But that's just, a really sort of simplistic answer. The real reason is that what happens if we raise one ion concentration? The other ion concentration goes down so that the product remains the same. So if we increase one ion concentration, the other ion concentration will decrease so that the product remains the same. And we could actually bring back in our concentration diagrams. Yes? And initially, let's say we dumped some A and B into solution. If I did the dump and stir method of making that solution, what could you say about the concentration of A and the concentration of B? They would be the same because every time I put in an AB, it separates into one A and one B. So I've got A and I've got B, and they're equal at the beginning. Let's say I increase the concentration of A. Yes? Now what is the concentration of A going to do? Yes. It's going to go back down, but remember it ends up higher than it was before. Yes? The concentration of B will, what does B do? Pardon me? Oh, we're not doing a rate diagram here. We're doing a concentration diagram. So if we have increased the concentration of A, we are now shifting to the left. B will also be shifting downwards. Okay, so B is also going to go downwards. So you can see that A is higher than before and B is lower than before. But if you multiply the concentration of A and B, they will be the same before that stress and shift and after the stress and shift. I don't think you're ever going to have to draw a concentration diagram like that, but you know, we got to keep reviewing stuff, right? Because eventually you'll have a final exam. It's nice to always see these concepts come up again and again. We are now going to deal with things that do not change the solubility of a salt. And you cannot change the solubility of a salt by adding more water. Yes? Remember, what is solubility measured in? What is the unit for solubility? Yes. Yeah, it's the molarity or moles per liter. So if we add more water, does more salt dissolve? So let's say I've got my beaker, I put in a bunch of salt, I've stirred it around, and there's some undissolved in there. If I add more water, does more dissolve? Are we silent because we're thinking about it, or are we silent because it's too simple, Ms. Spence? So let's say I have a teaspoon of salt, yes? And I have a half a cup of water, half cup, okay? And I put in that teaspoon of salt and I stir it around, not all of it dissolves, because it's not very much water, yeah? Now I take that cup of water and I fill up a garbage can full of water, okay? Now I take that salt and I dump it in there and I continue to stir. Does the rest of the salt dissolve? Yes, yes it does, right? Because there's more water for it to dissolve in. Yeah? So yes, I can dissolve more salt if I have more water. But the key thing is not only do I have more salt, but I also have more water. So have I changed the ratio of moles to liters? No, because I've increased the moles that are dissolved, but I've also increased the volume it is dissolved in. Yeah? And the moles per liter is the, solubility. So the solubility remains the same. I sometimes think about solubility as being like a hotel, okay? So if you have a hotel, it can contain, and say every room can only hold one guest, yes? We're just gonna be straightforward about that. Once all the rooms are full, can anybody else check in? Not unless somebody checks out, yes? Now, if I expand the hotel so it's a bigger hotel, yes, but it's the same, you know, floor plan and whatever, I can check in more guests, but I also have a bigger hotel. So the amount of guests per room is still the same. So that's kind of like what this is here, okay? It's not an awesome analogy, but it'll kind of make a little more sense when we start talking about adding the solid salt. Can we make more salt dissolve by adding more solid? So I've got salt in there and I've stirred it around and I've made a saturated solution and it will not dissolve. Can I add more salt to change the solubility? The solution, the solution is already saturated. If you add more salt, you simply have a bigger pile of solid. Yes? It's like that hotel is already full. And you've got a lineup of, I don't know why people would wait in the lineup outside of a hotel to get in, but let's pretend they're doing that. You've got a lineup of people waiting to get into the hotel. If you make a bigger amount of people waiting outside, that doesn't mean you have more rooms at your hotel. Doesn't mean you can fit more people in the hotel. You might want to, but you can't. I don't know, that analogy. Anyway, so, no. Because solubility is the concentration of a saturated solution. That was weird. Yeah, so you cannot increase the solubility. The maximum amount is the maximum amount. I do have a question for you though. This is interesting. And we're going to talk about rates, because let's review Unit 1 as well. If I add more solid, so I have a bigger pile of solid, what's going to happen to the rate of dissolving and the rate of recrystallization? That's worth thinking about a little bit. I would like you to talk about this one with your partner. And while you're chatting, I'm going to draw a little picture. What factor affecting reaction rates are we changing? Yes. We are changing the surface area, yes? Uh-huh. When we have a bigger pile of solid, what can you say about the surface available for dissolving? It's bigger. So if you say, okay, I can only dissolve off, let's just say it can just dissolve off the top. There's my dissolving. Over here, there's a lot more surface available for the process of dissolving. What can you say about the surface available for reprecipitation? It's also bigger because where can it recrystallize? It can recrystallize onto the crystal, right? It likes, little ions like to join with already made crystals. So you will have the same kind of thing happening here, right? We also have that same increase in surface area available for recrystallizing. So what happens to both rates? The rate of dissolving and the rate of recrystallization? They both increase. By the same amount. And if they increase by the same amount, what are we still at? Equilibrium. Oakley dokley. And I think that's it. Is that it? Yeah, that's it. So what we're going to do is, if you didn't get through all these exercises, you can work on them. If you did get through all those exercises, you can. These are extra practice, so they are optional if you need them, right? You don't have to do all of this. If you're feeling really good about complete ionic and net ionic equations, don't do all the extra practice because that would be boring and, tedious. So, need more extra practice on electrolytes? Hebden doesn't do an amazing job of it, so I would, take a gander over that section again, right, in your notes. If you do need practice on the NIE and CIE, Hebden has that. Qualitative analysis, you can do 3.1E. If you get to the 3.1E and you still need more practice, I think it refers you to some questions in Hebden, so you could do that till you're blue in the face. Okay. Changing solubility, you can do 3.1I, and that would just give you some more practice with what we just covered today. And when is your quiz? Tomorrow. And if you're bored, you can start on 3.2A. The worked examples are in the answer key. So if you're trying to, review dissolving for yourself or dilutions for yourself, then you can do that. Okay, and we'll just spend the rest of the class having a little work period. That's okay, we'll sort those out later. Yeah. a little bit break while you stretch out or go get a drink of water or go to the washroom, now would be a good time to do that. I know. I tell myself on the facilities, be right back.